So, hello again. My name is Benjamin Redford. I am the co-founder and CPO at Mayku. And this was me 7 years ago launching this thing on this very stage, which is called the Formbox. It's a small, powerful desktop vacuum former. We actually started the company, myself and my business partner Alex, with the lofty goal of localizing manufacturing. And I know what you're thinking. How are you going to localize manufacturing with a desktop vacuum former? And the honest answer is you're not. However, we did end up sort of setting a whole new market for desktop vacuum forming, which was very fun, and getting some really cool clients, like NASA, for example, who asked us for a more powerful machine, which we'll also get onto in a second. So for us, if we're trying to localize manufacturing, the sort of the holy grail, the most popular form of mass manufacturing technique would be injection molding. But as I'm sure you know, they are massive, they're very expensive to buy tooling for, and you need huge MOQs to actually make them cost effective. However, there is one technology that can get very, very high detail thermoplastic parts, but in much lower quantities. And that technology is pressure forming. Now, I have to tell everyone this because I have to tell everyone this, and pressure forming is not vacuum forming. Yes, we build a vacuum former, but no, pressure forming is not that. It's about 5 times more powerful and sort of equivalent to injection molding. So on the left, you have a vacuum formed part, and on the right, you have a pressure formed part. And I think the difference between the resolution of these two parts is quite obvious, right? And so as we're sort of learning about pressure forming, the sort of 3D printers of the world, the desktop 3D printers, the Formlabs, the BMFs, the incredibly highly detailed 3D printers are getting really, really good at making highly detailed temperature-resistant parts. And when you combine high-resolution 3D printing with desktop 3D printers, with pressure forming, you start to get some really interesting things. And so this is it's a 5mm thick HIPS part. It's essentially just like you would find on an injection molder. It's pretty solid. And it's actually been made using high-resolution 3D print and then put into the Multiplier pressure former. So we built a pressure former which is about the size of a large pizza box, or sits on a desktop about the size of a large pizza box, does about 5 tons of force, and can get down to sub 1 micron layers of resolution. And so that really opens up some very powerful benefits. It means that any 3D print that you put in there, whether it's a Formlabs print or even a tooled part or whatever, it's going to pick up sub 1 micron replication, and it's going to do that in a matter of minutes. So you could probably get about 26 of these little parts on the bed of the multiplier. This one you see here, just go back, is this big. And so, yeah, you can do some really, really finely detailed work with it, or some very large work with it too. And so what that basically means is if you've got a 3D printed part that might have taken you, 15 hours to print, you can then replicate that part in a matter of minutes very quickly. And you can do it in a whole range of different factory materials. So PMMAs, ABS, PXGs, whatever you might want. The stuff that you're usually manufacturing something in an injection molder, you can put into this machine. And all the way from very, very, very thin films, like this microfluidics chip. It's obviously also water resistant, so 3D printing might not be. So you can actually pass liquids all the way through these little kind of 10 to 15 micron channels. So you can start batch producing microfluidics chips. Or uber thick 5mm HIPS parts like this one, if you wanted to create a small batch of injection molded parts without having to put the upfront cost of 80 grand into tooling. And then also optically clear parts like this PMMA product casing. So 3D printers can sometimes have a tough time with doing completely optically clear parts, but 3D print it, put it into our machine, put in some transparent EVA, and you get very clear parts out the other side of it. And that's all from a desktop machine about the size of a large pizza box. And so that's the pressure former. It's 5 tons of force. The forming area is about 420 mil. Cycle times vary between 2 minutes to about 20 minutes, depending on the thickness of the material that you're using. You can go up to 5 millimeters thick materials, so very, very thick, down to about 0.1 mil of material as well. And it's super simple to use. So someone can take this, open it, get it out of the box, and start using it in roughly about 5 to 10 minutes. So that's the pressure former. And with it, combining that with high-res 3D printing enables you to create 3D, well, sub-micron details very fast, all at a fraction of the cost and time of outsourcing to other technologies, so injection molding, for example. But to make the machine work for their applications, engineers really need to be able to use it with hundreds of different materials, not just the ones that we provide. And so on the 26th of September, we're launching an accessory and new firmware. The first one, the accessory, is the reducing plate. And what that does is it condenses the forming area of the multiplier down to A4 or US letter size. That means any thermoplastic material supplier in the world usually cuts in straight lines. Our standard sheets are circular because we're dealing with so much pressure, and pressure wants to be spherical. Whereas with this, you can cut out any A4 or US letter sheet, place it into the reducing plate, place it into the machine, and you'll start getting perfect forms out every time. So it really opens up the whole world of materials that you can get. It also increases the thickness of material that you can put into the machine to above 5 millimeters. So we've gone up to 8. We're starting to test 10 millimeters, meaning you can get super thick parts, but still at sub 1 micron level of detail, which is really fun. The second thing is custom mode. This is a new firmware update that's going to be going out to all machines. So our machines are all Wi-Fi connected, means that we can send firmware and actually change the core functionality of the machine once they're actually out in the field. We can create new firmware profiles and send them to specific customers. And with custom mode, you'll basically enable the machine to learn, save, and edit any new type of thermoformable sheet material in about 5 to 10 minutes. You basically take your sheet, you put it in, you run the custom mode settings, and all it will ask you for is material thickness, what type of material you're using, what temperature it needs to go to, and then you just watch the sheet, essentially, and then you switch on a tiny little pump and watch it, and it will tune that perfectly in about 5 to 10 minutes. So then you will get completely consistent forms with your specific material going forward. You can also edit profiles afterwards, should you want to change them up and then dial up and down the detail that you want to get from those forms. So what does that actually mean for people who's sort of using it? Well, if you're in microfluidics prototyping and batch manufacturing lab like Rapid Fluidics in Scotland, and you're prototyping microfluidics on a 3D printer, it's actually very difficult to understand what those microfluidics chips are going to be like at mass manufacture without going to mass manufacture first. So if you prototype something in a high-temp resin, the liquids will act differently on a sub-micron scale on the resin than they would, say, if you were injection molding on PP, right? But to get to an injection molded PP sample, you need to spend 80 grand on tooling. And so what we found with these guys is that they can actually prototype their microfluidic chips by 3D printing them first, making a prototype in PP, which would be the final material that they would be manufacturing in, and then testing that and getting much more beneficial results, therefore saving them 80K, saving them the lead time that they would usually find on getting, I don't know, an injection mold made for however much money it actually cost them. And these actually work as well, which is pretty fun. I've got one with me here. If anyone wants to see it, I'll be walking around afterwards with it in my pocket. And this one's full of liquid that all squeezes around. And so the other side of this is a large food and manufacturing company that we cannot name. If you're injection molding your molds, your food molds for food-safe materials, or if you use a very particular blend of food-safe material, usually you'd have to injection mold your mold to be able to put it on the production line. Now they can 3D print their tooling, put it into the multiplier, and massively reduce their time to market of getting new molds out. And they're actually using these, first and foremost, to test molds before they go to mass production. And now they're actually looking at putting it into full-scale production inside the molds. So that's, yeah, in food-safe PET-G, enabling them to essentially test and rapidly iterate food molds very quickly and reducing that lead time. Third one, prototyping an electronics company. A large one, and if you're a consumer company that wants to prototype electronics casings in the final material, it's very important that you actually see what the CMF's like, what the feeling of the actual object is like. It's very difficult to do until you actually finish the injection mold and have it held in your hand. We've now enabled them to use, again, high-resolution 3D printing and the pressure former to actually produce small batches of products in the final material that they would be used in mass manufacture. So there's a whole bunch of different applications out there. We've just touched on 3: housings, microfluidics, food molds. There's also shadow trays and a bunch of other stuff. If anything is of interest or sounds interesting, I'll be walking around. My email's up there. Just come and have a chat, and I can also show you these things. And yeah, see what we can do. Thank you very much.